Every piece of technology you use today, from the artificial intelligence writing your emails to the digital art on your screen, relies entirely on microscopic switches processing electricity. These switches, called bits, are the foundation of modern logic. They have a very simple job. At any given moment, they must be exactly a 1 or exactly a 0. You can visualize a classical bit as a coin lying flat on a table. It is locked into a single state, permanently displaying either heads or tails. But the natural world doesn't operate in perfect, predictable 1s and 0s. Nature is made of fluid, overlapping probabilities, where things aren't just this or that, but a complex mix of maybe. This is why standard computers struggle to simulate things like new medicines or weather patterns. Using flat, rigid coins to represent the fluid complexity of the universe is an incredibly slow and inefficient way to calculate reality. To build a better simulator, we have to change the state of the coin. Imagine we flick that coin upright so it spins rapidly on its edge. This is a qubit, or a quantum bit. While that coin is spinning, it holds the mathematical possibility of being both heads and tails at the same time. This state of being in multiple positions at once is called superposition. This isn't just a metaphor. In the famous double-slit experiment, physicists found that subatomic particles, like photons, actually behave like waves of overlapping possibilities, passing through two openings at once until they hit the back wall and create this interference pattern. Now, imagine a second spinning coin appearing on the cable. Through a property called entanglement, this second coin becomes mysteriously synced to the first one. When two qubits are entangled, their fates are linked. If you stomp one coin and it lands on heads, the other coin, no matter how far away it is, will immediately land on tails. This instant connection between distant particles was so strange that even Albert Einstein was skeptical, famously calling it spooky action at a distance. Because these entangled coins can represent multiple values simultaneously, they don't have to work through problems one by one. They allow a computer to shape a massive landscape of possibilities all at once, finding answers in a single step that would take a standard machine millions of individual calculations. So, if you're a software engineer, this creates a unique problem. How do you actually write code for a spinning coin that represents a probability instead of a certainty? Standard code, like if this, then that, cannot control something in superposition. To program a quantum computer, we have to move away from simple logic and into advanced mathematical models. We represent our spinning coin as a vector. This dashboard shows the probability of heads versus tails. To influence it, we use matrices, number grids acting as wind pushing the spin. This shifts the coin's tilt, increasing the likelihood of the specific outcome we need. Quantum programming isn't about giving a machine definitive instructions. It's about calculating the perfect sequence of mathematical wind to guide the universe's probabilities toward the right answer. After all the spinning and the tilting, we eventually have to get a result. This leads to the final step, measurement. You cannot read a probability while it's in motion. The second you observe or measure a qubit, you force it out of its state of multiple possibilities. This is called the wave function collapse. It is the physical equivalent of a hand suddenly striking the spinning coin and pinning it flat against the table. The coin is no longer in superposition. It is now permanently locked into a classical state, giving you a readable 1 or 0 that you can use in your data. This is the core of quantum development, preparing entangled spinning coins, using grids of math to tilt their probabilities toward a solution, and then slapping them flat to see the result. To truly master these machines, we have to stop trying to force nature into rigid certainties. Instead, we have to learn the art of engineering the probabilities of the universe itself.